Welcome viewers. We know that Gauss's law states that the net amount of electric flux passing through a surface is equal to 1 by epsilon naught times the charge enclosed by the surface. This law relates the electric field at any point with the net amount of charge enclosed by the surface. Further, this law can be applied to find electric field due to uniform and symmetric charge distribution. In this program, we will try to find electric field due to a uniformly charged thin spherical cell. Now, let us try to solve a problem. A conducting sphere of radius 10 centimeter. So, you are given a sphere of radius 10 centimeter. Let us take radius of the sphere as capital R and it is 10 centimeter. Has an unknown charge, that means neither you know the magnitude of the charge nor you know the sign of the charge. If the electric field at a distance of 20 centimeter, that means the point is lying outside the sphere. So, the distance of the point is 20 centimeter, you can take it small r, and electric field at this point is given to you, which is 1.5 into 10 to the power 3 Newton per Coulomb, and this electric field points radially inward, and because electric field at this point is pointing radially inward, what does it mean? It means the sign of the charge on the surface of the sphere is negative. Charge on the surface of the sphere is negative. Now, you have to find the amount of charge on the surface of this sphere. Now, we know that electric field at any point outside is given by the formula 1 by 4 pi epsilon naught q by r square. By putting the values, you are given the value of electric field, which is 1.5 into 10 to the power 3. The value of this constant is 9 into 10 to the power 9 q, and the distance of the point, which is 20 centimeter. You can just convert it into meter, 20 into 10 to the power minus 2 whole square, and by solving it you can easily get the value of the charge on the surface will come out to be minus 6.67 nano Coulomb. Now, let us try to solve another problem. An early model for an atom considered it to have a positively charged point nucleus of charge Ze, surrounded by a uniform charge density of negative charge up to a radius capital R. The atom as a whole is neutral. For this model, what is the electric field at a distance small r from the nucleus? Now, let us try to solve it. Suppose this is our atom, which is having a nucleus. Now, the charge on the nucleus is given to you. The charge on the nucleus is plus Ze, and because we know that atom is electrically neutral, so the total amount of negative charge which is around this nucleus is also equal to total negative charge within this atom should be minus Ze, because total charge of the atom should be 0 as the atom is electrically neutral. So, minus Ze is the total charge which is present around this nucleus, Now in this question you have to find the electric field at a distance small r from the nucleus. Now this point may lie outside the atom and this point may also lie inside the atom. Now let us find electric field at any point P which is present inside the atom. Suppose this is your point P which is at a distance of small r from the center of the atom. First of all, let us draw a Gaussian surface, and by spherical symmetry the shape of the Gaussian surface should be a sphere. So our Gaussian surface is a sphere of radius small r. So first let us cut small area element delta s from this Gaussian surface, and the electric flux through the small area element delta s will be E delta s. It should be E delta s. Now what should be the angle between electric field and area element? It should be 0. But why? Because the charge on the nucleus was plus Ze and total negative charge on the whole atom is minus Ze. So the amount of negative charge which is present inside this Gaussian surface should always be less than this charge on nucleus plus Ze. Hence the net charge which is present inside this Gaussian surface is positive, and if the charge inside the Gaussian surface is positive, so the electric field due to this charge at this point P should be radially outward, and the direction of the normal is also outward. So the angle between electric field and normal at this point or at all the points on this Gaussian surface is 0. So small flux passing through this small area element is E delta s. Now to find total flux, let us sum over flux of all the area elements over all delta s, and because all the points of Gaussian surface are equivalent, so we can take E electric field outside the summation sign, it becomes E sigma delta s, and summation of delta s over the whole Gaussian surface will give you the total area of the Gaussian surface, which is 4 pi small r square. So this is the value of flux passing through the Gaussian surface using general formula of flux. Now let us find the flux passing through the surface using Gauss's law. From Gauss's law we know that total electric flux passing through a surface using Gauss's law, total flux is amount of charge enclosed divided by epsilon naught. Now first we have to find the net amount of charge enclosed by this Gaussian surface, and we can easily see that the charge on the nucleus is plus Ze and some negative charge is also present inside this Gaussian surface. So first you have to find the amount of negative charge which is present inside this Gaussian surface, and then we will add that negative charge with the charge of nucleus to get the total charge enclosed within this Gaussian surface. So total negative charge which is present in the whole volume of the atom was 4 by 3 pi capital R cube. Suppose the capital R is the radius of the atom. So total negative charge which is present in the whole volume is minus ZE. So negative charge is present in volume 1, unit volume, it should be negative charge present in unit volume should be using unitary method that you have learnt in your primary classes. This is the total negative charge which is present in unit volume. So the negative charge present within this cell, within the volume 4 by 3 pi small r cube will be minus ZE divided by 4 by 3 pi r cube multiplied by 4 by 3 pi small r cube. So pi cancels with pi, 4 by 3 cancels with 4 by 3. So what do we get? We get minus Z E R cube divided by capital R cube. This is the amount of negative charge only which is present inside the Gaussian surface. So the total amount of charge, now we can find the total amount of charge enclosed. Q enclosed will be equal to the positive charge of nucleus, that is plus ZE, and the negative charge, this one, that is minus ZE R cube by capital R cube. Taking ZE as common, we get 1 minus R cube by capital R cube. This is the total amount of charge enclosed. So the total electric flux passing through the surface using Gauss's law should be, by putting the value of charge enclosed in this formula, we get ZE by epsilon naught into 1 minus R cube by capital R cube. This is the total electric flux using Gauss's law. And we have already found out electric flux using general formula. Now equating the flux obtained in two cases, we get from equation 2 and 3 E into 4 pi small r square is equal to ZE divided by epsilon naught multiplied by 1 minus R cube divided by R cube. So the value of electric field comes out to be 1 by 4 pi epsilon naught. This will go in the denominator side into ZE, and we can take this R square into this. So we get 1 by R square minus R by R cube. So this is the final formula for electric field at any point which is lying outside the atom. And it is directed radially outward. If you want to write it in vector form, we can just multiply it by r cap. Now, from this formula you can easily get electric field at any point on the surface of the atom. If you want to find electric field on the surface of atom, you can just replace small r by capital R, and you will get the electric field on the surface is 0. If you want to find electric field at any point which is lying outside the atom, if the point P is lying outside the atom, this is our nucleus, positively charged nucleus, and if the point is lying outside the atom, suppose this is the point, then, and suppose this is the Gaussian surface, so the amount of charge enclosed in this particular case will be 0, because total amount of negative charge is equal to total amount of positive charge. So if we want to find electric field at this point P outside the atom, again you can find the electric flux through this Gaussian surface using two ways. Number one, by using general formula, then by using Gauss's law. And electric flux using general formula comes out to be E into 4 pi r square, and using Gauss's law electric flux comes out to be charge enclosed divided by epsilon naught. And because in this case amount of charge enclosed is 0, because atom is electrically neutral, so electric field outside the atom is 0. In this program, we have derived the expression for electric field at any point due to a uniformly charged conducting shell using Gauss's law. Can you use the result of this derivation to protect anything from outside electric field? We know that it is safer to be inside a car than under a tree during lightning in the sky. Could you guess the reason for this from the discussion during this program? Just apply your brain and think over it. Keep watching our videos to enjoy learning physics. Happy learning.